All right, if you're looking to really master the AS level electricity unit for Paper 2, then you are in exactly the right place. Today, we're not just going to go over the content, we're going to learn how to think like an examiner so we can turn those potential traps into easy marks. So, here's our game plan. We're going to start by cracking the code behind electricity questions. Then build everything up from the fundamentals of charge flow all the way to the secret weapons for solving pretty much any circuit. Then we'll wrap it all up with a clear strategy you can take straight into your exam. Okay, let's get right into it. Electricity questions can sometimes feel like they're designed just to trip you up, right? They look complex, they're packed with components, and you know that one tiny mistake can throw off the entire answer. But here's the thing. There is a code. There's a set of rules and patterns that once you see them, make every single question solvable. I mean, take a look at a circuit like this from a past paper. It might seem pretty intimidating right now. You've got resistors in series, in parallel, there's internal resistance. Where do you even begin? Well, the whole point of this explainer is to give you a step-by-step method so that when you see something like this, you don't panic. You have a plan. And that plan all starts with the basics. To understand the big picture, we have to get comfortable with the tiny, microscopic world of charge carriers. These fundamental concepts are where those first crucial marks are either won or lost. Let's start with the definition itself, because getting this wording precise is such an easy mark. Current is simply the rate of flow of charge. And what is charge? Well, it's quantized. Now that's a key term examiners are looking for. It just means that charge isn't a continuous fluid. It comes in these little discrete packets, each one a multiple of the elementary charge, E. Oh, and a quick tip. Be ready to state the SI base units for charge, which are ampere seconds. So on this slide, we've got our two key equations for current. The first one, Q equals IT, that's our big picture macroscopic view of things. But the second one, I equals A NVQ, lets us zoom all the way into the microscopic level. And this is where examiners love to set a common trap. Pay really close attention to that letter N. It stands for number density, the number of charge carriers per unit volume, which is a constant for a material like copper. It is not the total number of electrons in the wire. I'm telling you, confusing those two is one of the easiest ways to drop a mark. And here's a perfect example of how they test this idea. Take a look at this question. Two lamps are in series, right? So the current, I, has to be the same in both. They're made of the same metal, so the number density N is the same, and the charge per carrier Q is, of course, constant. So what's left? The only things relating current are drift speed V and area A. Since I is constant, V has to be inversely proportional to A. Think about it. If you make the wire thinner, the electrons have to speed up to get the same amount of charge through per second. That's the logic that solves these ratio problems in a heartbeat. Okay, now let's see how this all builds into the concept of resistance. See, resistance isn't just a number, it's a behavior. And in your exam, you absolutely need to know the characteristic patterns, the IV graphs, like the back of your hand. They're like the signature of each component. We've really got two ways to think about resistance. First, as a simple ratio. The potential difference, that's the energy transferred per unit charge, divided by the current. But more fundamentally, resistance is a physical property of an object. It's determined by its resistivity, ρ, its length, L, and its cross-sectional area, A. Longer and thinner means more resistance. Simple as that. And here is another absolute classic trap, taken straight from an exam paper. They'll give you the cross-sectional area, but often they'll give it to you as a diameter or radius in millimeters. You must remember to first calculate the area using pi r squared, and then convert your units from square millimeters to square meters. Forgetting either of those steps is a guaranteed lost mark. These three graphs, they are non-negotiable. You have to be able to sketch them from memory, and even more importantly, explain why they have their particular shape. The metallic conductor is your baseline. It obeys Ohm's law. The diode, well, that's just a one-way street for current. And the filament lamp, that's the really interesting one. So imagine you turn the page in your exam and you see this, blank axes. The question asks you to sketch the IV characteristic for a filament lamp. You know it's a curve, but which way does it bend and why? Getting this right isn't about memorizing a shape, it's about understanding the physics behind it. So here's the why. It's a chain reaction. As more current flows through the filament, it heats up. This makes the metal ions in the filament vibrate more and more vigorously. These vibrating ions literally get in the way of the flowing electrons, making it harder for them to pass through. That's what an increase in resistance is. So for the same increase in voltage, you get a smaller and smaller increase in current. And that's why the graph curves, flattening out towards the voltage axis. Okay, now for the heavy-duty tool. When you see one of those really complex circuits with multiple loops and branches, don't guess. Use your secret weapon, Kirchhoff's laws. They give you a systematic, foolproof way to find any unknown current or voltage. Now, what's absolutely essential to remember is that these aren't just some arbitrary rules. They are direct consequences of fundamental conservation laws. The first law simply says charge can't appear or disappear at a junction. What flows in must flow out. It's all about the conservation of charge. And the second law says that the energy supplied by the sources in any loop has to be fully used up by the components in that same loop. That's the conservation of energy. And this is the strategy that turns that confusion into a clear, repeatable process. Don't just stare at the circuit. First, label your junctions and your currents. Then apply the first law. Next, and this is a big one, physically draw your loops on the diagram. Pro tip, if you get a negative answer for a current, don't panic. It just means the actual direction is opposite to the one you guessed. If you're solving for two unknowns, you'll need to make equations for two different loops. After that, it's just a matter of solving them. Let's talk about the real world for a minute. Because, well, ideal batteries don't exist. Real power sources have their own internal resistance, and that changes how they behave. Understanding this is the key to explaining why the voltage you measure across a battery isn't always what's written on the side of it. This distinction is subtle, but it's so important. EMF, or electromotive force, is the total energy the battery provides to each coulomb of charge. Think of it as the total push. Potential difference, on the other hand, is the energy that's used by each coulomb as it passes through a component. So EMF is the cause, potential difference is the effect. So because the battery itself is made of materials that have some resistance, a bit of the energy the charges are given is immediately used up just getting out of the battery. We call this energy drop the lost volts. So the voltage that's actually available to the external circuit, the terminal PD, is the total EMF minus these lost volts. This simple equation perfectly explains why, as you draw more current from a real battery, its terminal voltage actually drops. And what's great is that we can use this relationship to find these values in an experiment. If you plot the terminal voltage against the current, you get a straight line. The equation V equals minus R times I plus E is in the form Y equals mx plus C. It's that simple. So the y-intercept, which is where the current is 0, gives you the battery's true EMF. And the magnitude of the gradient of that line gives you the internal resistance R. Okay, let's bring it all home. We've cracked the code, we've mastered the concepts. Now let's boil all of this down into a final, actionable strategy that you can take into your exam, turning those common traps into guaranteed marks. Here it is, your 4-point checklist for success. 1. Double-check every single unit, especially when you're calculating area from a radius or a diameter. 2. Don't just memorize the IV graphs. Understand the why behind their shapes. 3. The second a circuit looks complex, immediately switch to your Kirchhoff's laws strategy. And 4. Always remember that batteries aren't perfect and be ready to explain and calculate the effect of that internal resistance. You now have the tools and you have the strategies. You know the concepts, you know where the common traps are hiding, and you have a plan of attack for any question they can possibly throw at you. The code is cracked. The only question left is, are you ready to put it into practice?